First, let's talk about the process of converting keys to integers. So not specifically to a location that would be valid in an array, but just a numeric value. So before we do that, let's do a quick review of the pigeonhole principle. So you may have encountered the pigeonhole principle in a discrete math course or a math course, but if not, it's a pretty straightforward principle. So the basic idea here is if there are n items and m different containers, and we've got more items than containers, then at least one container will have more than one item. So it's commonly illustrated with a pigeon coop like the one over here. So there are a total of 9 different nesting boxes for our pigeons, so 9 nesting boxes, and we've got a total of 10 pigeons. So this guarantees us that at least one of these little nesting areas will have 2 pigeons in it. Now it could be far worse than that. Maybe all 10 pigeons end up in one little nesting area, one very crowded nesting area. The pigeonhole principle just provides some guarantees of that we have to have at least one of these boxes with more than one item if the number of items exceeds the number of locations. So that's going to be useful to us as we think about the idea of collisions with our maps and even with our just general hash functions independent of how they're used in maps. Okay, so as an example, let's go ahead and look at the Amazon product IDs that we considered earlier. So we considered these 2 different examples. So both of them begin with B0, and then there are several different numbers and letters. So the first one is B0, 7W, and so on. The second one's B0, 1I, 5, and so on. So I don't know all the details of how this is structured. Maybe there's some meaning here, but it looks like in one case the last digit is a letter, and in another case it's a number. It isn't clear if there are any restrictions on the particular letters or numbers that can be used. So I am going to simplify this a little bit. I'm going to assume that the initial stuff is always B0, and I'll kind of ignore that, but I'll focus on the other 8 characters. And I'm also going to assume that we can use any of the digits in any position and any of the letters in any position. So any combination of 0 through 9 and A through Z in each of the remaining 8 digits. So we've got 26 letters and 10 digits, so that gives us a total of 36 different possible values. So let's think about how many different unique product IDs we could represent with these 36 values. So if I were just using a single digit, I could represent 36 possible items. But if I've got 2 digits, for each of my first digits, I could represent another 36 items. And if I've got 3 digits, for each of my first 2 digits, I could represent another 36 items, and so on. So if we're considering a total of 8 different digits, the total number of unique product IDs we can represent is 36 to the 8th, otherwise known as about 2.8 trillion. So let's think about that. If we think about that in terms of like a number line, if we were to try and count all of the unique product IDs that were represented, it would basically go from 0 to about 2.8 trillion. Okay. Let's compare that to our data type that we're trying to convert these product IDs to. So if we're using a Java integer, it's a 32-bit integer, it can represent values from -2 billion to +2 billion, or a total of about 4 billion distinct values. So if you were to think about that in terms of a number line, it would just be a tiny, tiny, tiny fraction of the number line that we've already got. 0 to about 4 billion would just be a tiny fraction of that. In fact, it would be about 1/700th of it. Okay, so again, we've got all these distinct items up here, and we're trying to take each one of them and match it up with an integer value. And this is a classic pigeonhole problem. We've got far more items than the places that we're trying to associate them with. Okay, so by the pigeonhole principle, collisions of the hash function itself are almost unavoidable in many situations. Okay, so quick review of our hashing goals. Our hash function should be repeatable, it should be fast, and it should minimize collisions, but that may not be actually possible, and hopefully by minimizing collisions we can also uniformly distribute values throughout our table. Okay, so let's talk about some approaches we could use to convert data into valid integers. So now that we know that collisions may be unavoidable entirely, let's look at some options to actually convert a key, an arbitrary piece of data, into an integer. So we'll get 3 different options, but there are actually many others. So the first concept we'll look at is if we've got small, simple data type. So something that's less than or equal to 32 bits of data. So like an int or a comparable sort of data type. So in Java, a float or a short would also fit the bill here. So in this case, we can actually just convert the bits, the binary part of the data, to an int. And we can do this through something like a typecast, or there are some other comparable sorts of conversions that we could do for some data types. So if we've got a larger data type that's made up of multiple parts, we can somehow combine together those independent parts. So we'll briefly cover two different approaches to this. So the simplest possible approach is just to take each part and make it into a number, and then sum up the value that you get from each part. And then a slightly more sophisticated approach would be to convert the parts into numbers still, but use a polynomial of some sort to combine them together instead of just a simple summation. So we'll look at these in turn, starting with the simple combining parts approach. So in the simple combining parts approach, we convert the parts to numbers and then sum the parts. So we'll do an example here. So let's imagine we have letters, and each letter has a numeric code associated with it. So I've only done an example with just a couple of letters here. So we've got the letters O, P, S, and T, and they've got numeric codes 1, 2, 5, and 6. So Q, R, and S would have, Q and R would have codes 3 and 4. I just didn't include them in the table because they're not used in the next example. And we could give each letter of the alphabet a corresponding code. Okay, so let's go ahead and use that to convert some words using the sum parts. So let's think about the word pot, P-O-T. So P has a value of 2, O has a value of 1, T has a value of 6, add them all together, and we come up with 9. Okay, let's do a couple more examples. So pots, so we would start off with our 2, 1, and 6 from pot, and then we would add the 5 onto it for the S and come up with a total of 14. What about post? Oh, so that's the exact same letters. So the 2 and the 1, the P and the O, and all we've really done is we've changed the order of the S and the T here, but we're still summing them up, and of course the order of summation doesn't really matter here, so we come up with the same value. So this would be a collision, at least if we actually considered these to be separate things. If for some reason we considered these to be equivalent or interchangeable, then this may be desirable. But generally, if we're working with English words, these are definitely considered to be distinct words. And in fact, it's worse than that. We can come up with a lot of other arrangements of these letters that would lead to the same sum. So tops, ops, spot, stop. Okay, so there are a lot of potential collisions if we were to use this particular scheme and this particular code for English words. So this would work well if we were considering sets, where the order just doesn't impact the concept of equality. But if we're dealing with English words, this works really, really poorly because order is important. Okay, so this is sometimes appropriate, again, if you're dealing with the concept of sets, but oftentimes it isn't if you're dealing with some sort of a sequence where the order is important to the identity of the sequence. So let's look at the less simple approach. It's only mildly more complicated. So we'll still convert the parts into numbers, but we'll combine them using a polynomial. So letters will each still have a numeric code, and this time we'll combine them together by a polynomial with a coefficient in front of each term. So this is actually based on how Java converts strings to hash codes. This function is strongly based off of Java's hash code function, although it isn't exactly Java's hash code function. It's the same basic algorithm, but a few parts were changed to simplify the code and make it more legible. Okay, so basically what this does is it starts off with some value that's going to be the return value h. It starts off with 0. It does some sort of a check to make sure that there's some work to do. I'm going to go ahead and cross out that if statement just so we can ignore it and kind of focus on the body of the method here. So it's got a loop. It starts at 0, and it goes up through all the letters. And at each letter, it's going to extract the letter, and it's going to add it on to 31 times the previous running total. So the first time this executes, it's going to multiply 31 times the initial value of h, which is initially 0. So 31 times 0 is 0, and it's going to add on the value of the 0th character. So I'm going to designate the 0th character with a subscript. I'm going to write it as character _0. Then it's going to go back through the beginning of the loop again. It's going to move on to the second character, character 1, and it's going to multiply the current value of h by 31, and then it's going to add on that second character, character 1, and then it's going to continue through the loop and do the whole process again. It will multiply the existing values by 31 and add on the next character. Oops. And so on and so forth. Okay, so essentially this is creating some sort of a polynomial. In Java, it's actually using the Unicode character set. So it won't use those simple numeric codes that I picked earlier, but it will use numeric codes. And the polynomial for the hash code looks something like this for 4-character strings. So again, it takes the 0th character, multiplies it by 31, adds on the first character, takes that entire quantity, multiplies it by 31, takes that entire quantity, adds on C2, and so on and so forth. So let's look at how the words that I entered earlier would actually, what their hash code would be based on this formula, and using the Unicode values instead of the numeric code we used earlier. So POTS would have a hash code of 3446974. TOPS would have 3566014. OPS 3418144, and SPOT and POST. Okay, one of the things you might notice here is that these are all unique. They're not true collisions, but another thing that's kind of interesting here is that they do also all end in 4. So there's some similarity, but not quite true collisions. So depending on how we follow this up in the next step, the converting an integer to a valid location, the similarity here may or may not be a problem.